Hi everyone. In this presentation we are going to look at the second portion of geological maps and cross sections. So in this example I'm going to use the same map that you guys are going to do the practice, and it's a part of lab book. First of all, what you should do is paint your map, and for doing that you need to choose a right colors. So of course you can paint with any colors you want, but it's gonna make more sense if you follow kind of standard rules and choose the right colors, because as you see here in these three maps, the one in the far left, it looks better because the contrast of the colors is much better, and the color is chosen. It makes more sense. But the second one, the middle and third one, maybe the third one, it looks a little better than the second one. These two, it's kind of chaotic and you cannot really see the rock relationship easily as you see here, right? So look at this one, right? This is the unconformity that we have, right, in this map, like one of those examples I showed you, but it's not quite clear here more to compare with this because the colors are so close. It's not that easy to distinguish. Or look at these faults, right? Look at these strong changes, or even though the colors are somehow similar to compare with this, because here the colors are different, but they don't really show the structure variation along the cross section as it does here, right? So if you go with this kind of colors, that would be good. And the guidance for how you can paint your map is indeed is this chart. So this is a geological time scale, the colors representing different time period, right? And you need to choose the same color for a specific time range, right? So if you're using like yellow and orange, it means you're presenting Cenozoic units. If it's green, blue and purple, you are in Mesozoic. And if you are in the dark colors, you are actually in Paleozoic and Precambrian. So you're going to use the same type of colors in your map. Then not only it's going to give a better look to the map, also will define the relative time relationship between the units on the map as well. So first of all, get that one colored. So here I'm gonna show you the steps that I take normally for providing the geological maps and cross sections. Mostly in this presentation I'm focusing on cross sections. First of all, as you learn, you're gonna draw the topographic section, and then the next step you're gonna draw the faults. So what you do is you take a piece of paper and place it from A to A prime, and you see topographic contours and make a note for each contours with the value, right? So if I'm gonna provide a quick topographic cross section, I put a piece of paper here and I make a note for 4400. Right, you go one by one. For instance, here's 2800, right? Here it's about like 3000, I guess, right? You see, this is 3200, right? This is 2000, 2400, 1600. You make a note like this on your paper, and then when you are here, you can actually, obtain your cross section like that, right? This is step one. Step two is finding the faults and plotting them. But for plotting, you're going to use the apparent dip, right? Because at some locations, maybe your cross section it's perpendicular to the fault, maybe it's not. For instance, here you have two faults. Let's call this one fault 1 and this is fault 2, and your cross section here it's perpendicular to the fault strike, but it's not perpendicular here, right? And you need to use the apparent dip. So I think you know so far how to do it. Again, use the same piece of paper, place it between A prime, make a note for fault 1 and fault 2, and take that piece of paper and place it here, and then make a sign for F1 and F2, and then you know that the faults are dipping towards west. Okay, if you go to the map, let's see where we have the map. You see the fault is dipping towards west. The fault is dipping towards west. Okay, 45 degrees, 75 degrees, right? These are the one that is reported here, but these are, the dip of the fault, right? It's not the apparent dip. So you need to calculate the apparent dip for at least for fault 1. Maybe it's gonna give you a difference of 1-2 degrees, but there are some specific cases that they varies with the large values, but for this one it's fine. So it's dipping towards west, 45 degrees, let's say, the same apparent dip somehow, or 44. So you draw the fault and you draw the fault, right? 75 degrees and 45 degrees. This is step 2 that you should do. All right, so step 3, obtain the type and the sense of the fault movement and add the sign of the movement on the cross section. So I need to know, is this fault is a normal fault or reverse fault? So how you do that? You need to look at to the observations. Let's look at this. So this is the fault 1, right? It's dipping towards west, and let's see the is there any kind of observation you can use to figure out is this is a normal fault or reverse fault? I think the only observation here is the age relationship along the fault. So you need to look at what is the age of TR, what's the age of TTS, right? Look at this contact, what's going on here, or the contact here, right? You have, you need to concentrate along this to see what kind of age relationship we have, right? Or we can look at, the TM, right? The TM here, it's next to TR here, right? Or TMM, TR. So let's look at the age relationship. So the TR is tertiary or a part of Mesozoic. TMM is also a part of tertiary, but it's older. Okay, this one is sitting in Eocene and TR is in Miocene, right? So you have let's place it here. Okay, you have the older rock here. This is the old rock, and this is the young rock, right? So this is young, this is old, the fault is dipping that way. So how you can have the old rock to the earth's surface, right? And in the hanging wall, the only way of doing this is this block. If this block moves towards upward, then it can be eroded away and the older units can reach to the earth's surface. So if the hanging wall is moving up, then this is a reverse fault, right? And how about this one? This is again is a fault. You can take any of these contacts you would like. So let's again take the TR and look at this color. I think this is TTS, right? This is again let's put this one TTS. So here is TR is younger than TTS, so and is dipping that way, right? The fault is dipping towards west, and here you have the foot. This is the hanging wall of this fault, and this is the footwall of this fault, right? And you see all units are exposed at the footwall, so this unit came upward So if the footwall moves upward, then this is going to be a normal fault, right? This is a reverse fault and this is a normal fault. So next, what I need to do is, indeed, let's see if I have a cross section here. Yeah. So what I need to do is putting a sense of the movement here, right? This is a normal fault, right? And this is a reverse fault. So you need to show this, okay, as a step 2. And after that, let's see what we should do. Obtain the type of the sense that we did this, right? We talked about that. Number 4, try to understand overall structure style. Maybe drawing a rough sketch will help most, right? So what I'm gonna do before diving into the details, I would like to see what kind of structure I have, right? So I'm gonna change the, okay, let me change to blue, and let's say I had a fault here, right? This is a reverse fault, right? Here I had a normal fault, right? I'm doing like a quick cross section here. What kind of structure that you see here? This is TM, this is TMM, so this is TDD, right? If you are moving from here to there, or from here to here, okay, you are moving from TM to TDD. So what kind of age relationship we have? So TM is here, right? And then you have TMM. The second is this. The third one is TDD. So you are moving from old to young, right? So this is old. This is, let's say, this is young, and this is younger, right? So if you're gonna put like a 1, 2, 3, okay, the core is older for sure. You have a big anticline here, right? So here you have anticline. How about here? Here you see just TR. There is no dip reported as you see here, and you're gonna see, okay, at some places the topographic contour line are somehow parallel with the outcrops. So if there is no information of dip direction given on the map, you can assume this is a flat horizon. So here what you have, it's almost flat, at least at the surface, but maybe towards depths the structure form will change, right? So we're gonna investigate that one as well. So again here, let's see what we have. We have TDD. We know TDD is younger than TM, younger than TMM and TM and TSS, right? So what's happening here, if this is, let's say, if I take this one as a core, right, it's getting older that way, it's getting older that way, right? Or if you take this one here, it's getting older that way, right? Or older this way, right? So you have young in the middle and old, you know, in the surrounding area. So this is showing you have a syncline here, and then here you see everything, it's flat, right? You probably, if you look at, you know, closely to the lower part, you're going to see topographic contours are somehow following the same outcrop, you know, contours, right? So here you have a kind of angular unconformity. Here you have syncline, probably. Let's see what we have here. Again, is TDD, TMM, TM, right, and TTS, right? The same stuff here. Okay, it's getting older that way and older this way, right? The same as this. So you have another big syncline here, right? And for sure, below this angular unconformity, you're gonna have one big anticline, right? This is how it looks like, okay, a general sense of the area, right? So I need to make this image in my mind, and then I can go to the details and I can improve the quality of the section, right? So let's see what we do in, you know, number 5. So again, always go back and forth to the time and the outcrops. That's a key, right? And then step 5, you know, draw unconformities and complete bedding in the section only above the unconformities, right? So what you're gonna do, and this is number 5. And let's see what's number 6. It's the time to complete section by working on the units below the unconformities, right? And obtain apparent dip for the units. This is important. As I said, sometimes, as you see here, okay, the orientation of the bedding is like that, and it's not perpendicular to the cross section. So you need to use apparent dip of the bedding, how it looks like along the cross section, right? So you need to do that. If the angle is so small, like 5, 7 degrees, 10 degrees, you can ignore calculating the apparent dip because it's not going to change much. It's like maybe 1, 2 degrees, and that falls into your error range. But if the angle is about, more than like the one that here you see, the 90 degrees is turning to 45, which means there's a change of 40 degrees, then you need to calculate the apparent dip, because that's going to change at least 10, 15, or maybe 20 degrees in the dip of the units, how they look like along the cross section. So what I'm going to do here, I'm going to show you a couple of cross sections. So this one was provided with one of the students. So as you noticed here, right? So what we have here indeed is anticline, syncline, and here anticline, syncline, anticline, right? This is what we obtained as a large picture. But how you're gonna draw exactly these units, you're gonna do in details. And as you learned, first you do the cross section, topographic cross section. Second, you do the faults, you find the sense of the movement, and then after that you plot the unconformities, right? So for instance here, you need to, actually this one is here and AA prime is here, right? So the THD, indeed from here, I know this unit is flat because no information is given, but the units below, they have a strike and dip. This is flat. You can make, a note for these two outcrops. You can place it here, and then you can draw the straight line, and that shows the THD. So you can go along this. If you see a flat horizon, yes, in this block, in the middle block, but you have TG, you have TR, right? TG and TR, they are almost flat. So you show it, where crossing the section, right? You make note and you can place it along topographic section. Here it seems it's a little bit tilted, but it's not more than like 10-15 degrees, right? And the reason why it looks a little bit more tilted here, it's because the exaggeration along the z-axis, right? When you are working practical, you can ask a question about this in your lab section. I think it's easier to explain in person rather than in video. So if you have question about the exaggeration along the z-axis, ask some questions. And then we have another unconformity here, right? It starts from here to here. And why? First, there's a few observations. One is the top, this let's say the rock contact. Okay, these are parallel, but these are also parallel, but they are crossing each other here, right? You see this one along this line. So the units here striking like that, here striking like this, they are crossing. So this is angular unconformity. The same thing here, right? Here they are like this, here they are looking like that, right? So there's a intersection here. So that is the angular unconformity. And then you complete this portion. Next step is completing the outcrops above the unconformity. So here it was only THD, it was easy. Here you have 2 units, TG and TR. Here you have like 3 units, TG, TR, THD. Complete those, and after completing this, you can go to the big picture, and now you can use these numbers to complete the the cross section. And again, when you want to, because your cross section, so an example here, okay, where the contact between the yellow and the brown is sitting, because now it's covered by THD and I don't know where they are. But what you can do, you say the contact is here, the contact is here, and probably this is going to be something like that, right? You just make a dash line, or this contact, probably it's going something like that, right? So you guess, you do the best guess, and you use these contact points to complete the structure below the unconformity. About this one, as you see, everything is covered by this unconformity. How you know you have the syncline here? You need to look at the big picture. So you need to go, I go back to my map. All right, so our cross section is here, okay? The section or the big structure, it's covered here, you cannot see it. But what you can do, you can go a little bit far from the section location where the structure is cropped out. So you are not going only look at the things along this line. You need to look wider and see what's going on in the area, right? So you see the structure here is cropped out. So it's TDD, TM, TMM, and TM, and TTS. And TTS is older, okay? This is younger, right? If you put like a time 1, 2, 3, 4, and again here you have 3 and 2, right? You see this is a syncline, right? And you see these units are getting close, and you see this V shape here is closing, right? So this is for sure it's syncline because the core is younger. This is a V shape at the end of structure, and this shows this syncline, it's plunging towards north, right? If I show with the with the sign, this is plunging syncline. So for sure this syncline, okay, it's continued below this unconformity, and still you're gonna have the syncline here. If you look at the details, you're gonna see this is the overturned syncline, and both limbs are dipping towards northwest, right? So as you see here, this is overturned structure, and both are dipping towards northwest, but this section is west-east, so you see the units are dipping towards west. And the same thing for the rest of the section, right? So you can guess that TM and TMM contact is here. The next contact between TM and TMM is here. Probably, okay, there is something like that is here, or the next one, okay, it's probably going something like that. Okay, let me clean this up and then redo it. I'm gonna do it with the black. So probably this contact goes like this. This contact is going something like this, right? And similar to this one here and this one here, right? These are a kind of traces for the strike of the bedding below the unconformity. So if we know this contacts, right? So this one, as you see, it's a little bit covered here, and then gets out here, and then goes back to this, right? So you see again, right? Here for sure we have plunging structures, right? So you see this kind of V shape that they are reaching, okay, or they are exposed at the end of the structures. So TDD, TTS, this is young, this is old. So this is a syncline, is dipping, or it's plunging towards northeast. Here, this is again, this is young, this is old, this is another syncline dipping towards northwest. And the one that is covered by the unconformity, this is TTS here, right? Below the unconformity, the core is old, the limbs are young, right? So if it's young in that direction, that's gonna be the core of the anticline, right? It's getting younger to these directions. So by knowing the age relationship and having a big picture, now you can use, okay, those information to complete your image. So about the, what is the depth of the units here below the unconformity, because they are not exposed to the surface and you don't know, okay, which one you can use. In that case, you can actually get, information from the closest unit, okay? Take the one that it seems, or it makes more sense with the large picture, all right? So by knowing that, you can complete your cross-section. This is another cross-section, CC prime. All right, in one side you have sedimentary unit, in the other side you have metamorphic units. Again, here you see there is a flat horizon here up to here. Then you see, the strike and dip is reported. So here we have the unconformity, contact, angular unconformity, young units over the old units. Again, another unconformity here to here, right? These units are above the unconformity and these are below the unconformity. So these two are shown here, right? And what kind of images that we have? We have TM here. We have, let's see what we have below TM or above TM. This is TM. Below we have TTS and we have TMM. So this is TMM, this is TM, this is TTS. It's getting, younger towards the core. This is syncline. Right, you see here, and what we see here again, it's you see this unit is TTS, the next one is TBB, the next one is TE, right? The entire unit here is just dipping towards west, and it's just getting, older and older. So you don't have any structure covered by the unconformity. It's just the limb of the large structure is covered, right? So you see TTS, TB, and TE. And one thing you probably noticed, the color in the cross-section doesn't match to the map, and that's because one student did a good job on the map and the bad job on the cross-section, and somebody else did a better job on cross-section. So I'm using the best one, so the color doesn't match, but in terms of the quality of the work, okay, the one that is done this cross-section was looking much more better. That's why I used that one to show you. And of course, you see, for instance, here, one fault is just, covered by the unconformity, and how this student knows there is a, possible fault below the unconformity because she looked at to the big picture, right? Let's look at to, this fault, right? Maybe I get a better, let me go to this one here, right? Let me clean up everything. So we were looking to, C prime, and we were looking here and how we know there's a fault here, because if you notice this fault, okay, is exposed at the earth surface and it's just stopped here, and this is because it's covered by this unconformity. But for sure, this fault, okay, it's covered and exists, below this unconformity. So as I said, you are not going only to look at along the cross section, you need to know a big picture and include everything that you think it makes sense to have it in your section, right? On the other side is the last point. So here to here, let's see what kind of units we have. You see superimposed folding, because the units, okay, we will talk about that later on when we are talking about the folding. But as you see, the strike and the dip of the folds actually showing these observations. So you see this kind of V structure here, okay, about if I draw a line along DLM, it goes like that, but it's not a straight line. The DLM itself, it's bended on the in both direction. One, it's bended along, okay, this line, and one is bended along this line, right? It means we have two set of the compressional systems applied in the area. That's why you have superimposed deformation. And the reason for that I wanted to show this portion of the section, it's because we are dealing with the with the metamorphic rocks. Look at the OMD, OMT, SM, and DLM, and all of them, okay, are schist, okay, quartzite, slate, okay, quartzite, right? So all of these units, the old units, are metamorphic rocks. Look at to what we have here. So red unit, okay, the one that you see here and here, right? So these two units, all right, are indeed granitoid, right? The rest is older rocks, right? The rest is older rocks, so it means this granite, okay, is intruded inside these older units. So you can imagine that along this you can have, this is the intruded, okay, this is the intruded contact between the older sedimentary rocks that they are now metamorphosed and the big KDT outcrop, which is the batholite, right? So if you go back to the cross section, all right, here, as you see, OMD and OMD, OMT, SM, and DLM, right, which expose along the cross section, how the contact is changing between these units to KDT. Okay, you can choose any irregular contact you want, because no one knows how it takes place, right? Because we don't have the subsurface data, then you are free to put any kind of contact you want. I just wanted to show you how you go step by step. You're gonna learn more in the lab section. Thank you very much, and see you next time.